Hey, all you cool cats and kittens. That's my very best Carol Baskins impression, so just let me live, all right? Um, I just want to be completely transparent. Got this image off the internet because everyone is hashtag obsessed with Tiger King right now. And I actually stole this from my great friend, Ashley Perez. She made the Hey, all you cool cats and kittens thing, I think. So just wanted to give her credit. And I wanted to say, what's up, what's up, what's up, my pre-calc people. Today we are finishing section 7.1, the fundamental trigonometric identities and families of identities. So I kind of broke it into 2 days just to kind of ease us back into things because these can be a little bit tricky and can at times feel overwhelming. So today we're going to finish that section up. And then guess what? 7.2 is more proving. So the rest of the chapter essentially boils down to proving a bunch of trig identities. So what you guys will see on your hyperdoc today is you have a 5-minute warm-up video to watch. It's not an Edpuzzle one. It's just straight up from YouTube from a guy that I really like the videos that he puts out. But it's just a lot of, I think it's 5 tips and tricks when proving trig identities, and kind of goes over just like in general what you can do to manipulate trig identities and arrive at the goal of proving the equality, which is what we did a lot of in 7.1 day 1. So to recap a little bit of what we did last time we met is we were starting the process of trig proofs, and some of you guys are like having flashbacks to geometry proofs and are like freaking out and being like, oh my god, I don't know what's going on, and stressed out. And some of you are super pumped about proofs because if you're a total nerd like me, they are super fun. They can also be incredibly frustrating at times, don't get me wrong, but they are like a really good problem solving, obviously, element of math, but they're one of the things that gets me super excited. So we started off, check out this little number line here. The first thing we did, I don't know why I called them stages. It was just the PowerPoint that I had. But the first thing we did was we identified some key things that we were going to be using. Those key things were the reciprocal identities, ratio identities, and the Pythagorean identities. Those are crucial. We can't really do anything without having that key piece of information laid out for us, and kind of defined reciprocal identities in a different way than we had before. Ratio identities a little bit different than we had before, and then expanded upon some Pythagorean identities. Then the second thing that we did was we manipulated the Pythagorean identities. So like the things that are equal to 1, that's the best way that I can remember which ones are the Pythagorean identities, since there's so many, like sine squared plus cosine squared is equal to 1. We manipulated those to create families of identities, and this just added to our toolbox. So we manipulated them around. We solved for one of the variables. We took the square root, those types of things. The next stage that we talked about was we discussed like how you should prove identities. And this is where I was like, all right, you're either going to take the left-hand side and manipulate it and turn it into the right, or you're going to start with the right-hand side and manipulate it with algebra and tricks and stuff and end up at the left-hand side. The next part thing we covered was we used some specific strategies to actually practice and prove some identity. So we used algebra with like a specific rule that was given to us, or a specific information direction in the problem that helped us verify an identity. So we won't always be so lucky to have directions on how to prove things. But starting out, it's very helpful for us to have a specific rule to start off on the right foot. Then we explored another strategy, which was to use a special product to verify an identity. So I think the examples that we did were expanding a binomial. So like a plus b is a binomial. A plus b quantity squared is equal to a plus b times a plus b. And then we expanded that out, used some sort of manipulations, used a product or something like that, to manipulate our equation and get us eventually to where we wanted to arrive. So that's where we started off. And alas, today we have more strategies to help us continue to complete trig proofs. Yeah, so let's get into them. I'm only going over 2 examples today just because they can be overwhelming. And we did quite a few the last time we met. And I gave you guys a fair amount of practice, not overload, but I gave you a little bit more practice than I did on the first day because quite honestly, the only way in which you're going to get better at any of these is practicing manipulating things, noticing things that are equivalent, noticing substitutions that would work in your favor, thinking smarter, not harder. Although, I mean, I'll have to admit that I even work really hard sometimes, and they take me a fair amount of time on my own as well. So, one of our new strategies is writing one trig function in terms of another. And like, this shouldn't come as too much of a surprise because we did talk about this the last time that we met. Like, remember we had tangent and we rewrote that in terms of another trig function that we hadn't done that before. So the main idea for this strategy is that any one of the 6 trig functions can be written in terms of the other ones using those fundamental identities. That's kind of like our basis for everything. But the purpose of this is that the process allows us to practice working with those identities, kind of like getting our hands dirty, right? It highlights how each function is related to one another, especially the reciprocal functions. It has practical applications in verifying more complex identities, which if y'all are going to calculus, that is what you need. There are some things that we just simply cannot integrate, and we need to perform trig substitutions, and that's when this is going to come in handy. And you'll be familiar with making these substitutions in order to kind of finagle your way to get through to a final answer, or a final product, or a result that you're allowed to perform in calculus. So writing one trig function in terms of another. For this particular example, we don't have a statement to prove, which is what kind of makes these a little bit harder. So it's kind of like starting from scratch. So here's the first example that we're going to have. Or again, we're going to write one trig function in terms of another. So our example is to write cosine theta in terms of the tangent function, and that is literally all they give us. Absolutely nothing else. So we kind of have to sit here and brainstorm a bit. Like, okay, starting from scratch. Well, what do we need? I kind of like to write a goal off to the side, especially while we're practicing these. We need cosine to be written in terms of tangent, right? So the goal is to somehow either go from tangent to cosine, cosine to tangent, something like that. But I need cosine of theta equals something with tangent on the other side, or tangent of theta equals cosine of something on the other side. So that's my goal. Like, I need cosine to be written in terms of tangent because that's precisely what the example and the problem is asking. So upon thinking about this, I realized that cosine theta and tangent theta have secant theta in common. Specifically, the Pythagorean identity, secant squared theta is equal to 1 plus tangent squared theta. So I'm thinking about my Pythagorean identity because they kind of lead down a good path. And I notice that I do have tangent in there and I have secant, but I know secant is the reciprocal of cosine. So that's why I chose to use that Pythagorean identity. So although I don't specifically have cosine of theta equals something that's directly equal to tangent theta, that would be far too easy, of course. I do have an identity that has the tangent and then has the reciprocal of cosine. So that's usually a pro tip of what we're going to want to work with here. So I'm being a little bit more formal in my proofs, kind of like I'm back in college, the good old days. So this was a lot to type out, especially the next example, but I hope you guys appreciate it. So in college, when we were writing a mathematical proof, we would always start by writing proof on the left-hand side and underlining it. So usually I'll say given something, but we weren't really given a particular set of directions for this example. So sometimes we'll state a given statement or like what we would want to achieve. Here, I'm just going to start off by saying start with secant squared theta equals 1 plus tangent squared theta. That's our Pythagorean identity. Then, if we take the square root of both sides, the square root of secant squared theta is equal to the square root of 1 plus tangent squared theta. And the result of that move is going to be secant theta is equal to plus or minus the square root of 1 plus tangent squared theta. Now remember, plus or minus is referring to where our function might be positive or negative depending on the quadrant that it lives in. Also notice that secant theta is equal to plus or minus 1 plus tangent squared theta is a family identity of that original Pythagorean identity. Now, in order to get to where we're going, I know that cosine and secant are reciprocal functions. So I know cosine theta is equal to 1 over secant theta, and vice versa. Secant theta is equal to 1 over cosine theta. I want to use this to my advantage because right now I have secant in terms of tangent, but I don't need, the goal wasn't to have secant in terms of tangent, it's to have cosine in terms of tangent. So I'm going to use this fact to get to where I need. So since cosine of theta is 1 over secant, and secant is 1 over cosine, I can kind of rewrite the statement secant theta equals plus or minus 1 plus tangent squared theta by taking the reciprocal of both sides. Cosine of theta is then going to be 1 over plus or minus tangent squared theta because cosine and secant are reciprocal functions. And now you'll see that I have cosine in terms of tangent in some way or another. I officially wrote cosine theta in terms of the tangent function, which means I'm completely done with my mathematical proof here. Well, it wasn't so bad. Sometimes they're not so bad. Sometimes they're a little bit longer, though. So that's one way of writing trig functions in terms of another. Usually kind of start out with a Pythagorean identity, maybe use a family identity, and then see ahead of time before you actually do your proof if there's a reciprocal that you can slip in there to get to where your end goal is. Another on a related note, another strategy that we're going to use is using a known value and quadrant analysis to find other function values. So we're still going to use a function and rewrite it in terms of other functions, but now we're talking about a very specific known value. So I'm going to say, like, I don't know, maybe tangent of theta is equal to a specific like number over a number, a specific ratio, right? And then we're going to analyze which quadrant it's in to find the other trig functions in relation to that. So the main idea is that the fundamental identities enable us to find the value of all 6 trig functions at angle theta. This is generally true for any trig function at an angle theta. So what we've got to do in this instance is we're going to be given usually a trig function that we know, like, sine of theta equals 1/2 or something. Then it's going to ask us to find all of the other trig functions. And since there are 6 total, the other 5. But we have to kind of go back to the basics. When we first started talking about all of this stuff, we got to visualize where we are in terms of our terminal side or our ending side of that angle in order to be able to determine the appropriate sign, kind of like when I had the plus or minus square root in the last example. Just because we need to decide if this ratio is going to be positive or negative, dependent upon where our terminal side of our angle ends. So let's try it out. And these, as you might guess, can tend to be a little bit longer, but it's not that the difficulty is that much more of a stretch. It's just more time consuming because we're finding more things. Instead of proving that one thing is equal to another, we're saying, okay, given this, now tell me what all of the other trig functions are for that same value of theta. So instead of proving one thing, which can be tedious and tiresome and take a while, we're proving 5. We're finding 5 things. So Oop, yes, before we move on, I just want to remember to remind you guys that we have this little picture of our quadrant, right? ASTC, all students take calculus, right? And this stands for all of the functions are positive in the very first quadrant. The sine functions and sine reciprocals are positive in quadrant number 2. Tangent and reciprocals of tangent are positive in quadrant 3. And cosine and cosine's reciprocals are positive in quadrant 4. So every single trig function, all of them are positive in quadrant 1. There's no way to get a negative value at all. Sine and cosecant are positive in quadrant 2. Tangent and cotangent are positive in quadrant 3. Cosine and secant are positive in quadrant 4. All right, so let's get to the second example of our lesson today using a known value. So they're going to give us something in quadrant analysis. Where is it living? To find out the other trig function values. So here's our example. Given that cotangent of theta is equal to negative 9 over 40 with terminal side of theta in quadrant 4, find the value of all of the other 5 functions of theta. So the very first thing that we have to think about is brainstorm. What do we need? What is this question asking us, and what is the goal? It's asking us to figure out what sine of theta is equal to, cosecant of theta is equal to, cosine, secant, and tangent of theta. What are all of those 5 trig functions equal to for this particular example, for this instance that's given to us? Like I said, that we need to visualize. Notice that up little bopped our quadrant here and our triangle in quadrant 4. And since I'm given that cotangent of theta is negative 9 over 40, I can label my sides 9 and negative 40 based on SOHCAHTOA. And let's get started on our proof. So we are given that cotangent of theta equals negative 9 over 40. My goal is to find out what sine, cosecant, cosine, secant, and tangent are, right? So tangent of theta is negative 40 over 9 since tangent and cotangent are reciprocals. That's a reciprocal identity that we know. So I started off with cotangent. I've got my first trig function right away just because of the reciprocals. Cool. Now, observe that secant of theta can be found by using the Pythagorean identity. And the Pythagorean identity that I'm talking about is that secant squared of theta is equal to 1 plus tangent squared of theta. That's the Pythagorean identity that I'm specifically discussing. So if I have secant squared of theta equals 1 plus tangent squared of theta, I can substitute in the value of tangent that we got from the reciprocal of cotangent. So secant squared of theta equals 1 plus negative 40 over 9 quantity squared by direct substitution. That was what tangent was equal to. And so I have tangent, but it's squared. So I've just subbed that guy right on in. Then I'm going to do next just a little bit of algebra. Secant squared theta equals 1 plus 1600 over 81. That was just me squaring negative 40 over 9. Going further from there, if I add 1 to 1600 plus 81, getting a common denominator, I get secant squared of theta equals 1681 over 81, 1681 over 81. That's just by simplifying my quantity. And now, remember, I want to get just I have cotangent and tangent, so I'm really, really close to having secant. So let me find secant, and then I can find cosine because they are reciprocals. So if I take the square root of both sides, I get secant of theta is the square root of 1681 divided by 81. And if I simplify that, the top reduces to 41, the denominator reduces to 9, so I have secant of theta equals 41 over 9. That is my third. Well, actually, I was given one. So 1, 2, yeah, that's my third out of the 6 trig function that I've been looking for. And all I did was notice that since we're in trig or in quadrant 4, because this really should have been plus or minus the square root. I realized that if I'm in quadrant 1, 2, 3, 4, quadrant 4, all students take calculus. Things that are cosine or the reciprocal of cosine, which happens to be secant, will be positive. So secant of theta will be 41 over 9. And also by reciprocal functions, if secant of theta is 41 over 9, cosine of theta is 9 over 41, just by reciprocal functions. So I have 1, 2, 3, 3 out of the 5 trig functions that I was asking to find, and I was given cotangent of theta equals negative 9 over 40. So to finish this up, I need to find the other 2 trig functions, and I can find these in a similar way. Now, of course, there's usually a few ways in which you can do trig proofs, but I urge you to just be a little bit careful on what you're putting out there, because sometimes we can think we're proving something, but we're going in a circle, or sometimes we're substituting in something that isn't quite equivalent. So since I know that this one works perfectly, I used a Pythagorean identity and just substituted something that was given. I'm going to use that same process to find sine and cosecant, since I have cosine, secant, tangent, and cotangent. Cross them out. All we have left to find is sine and cosecant. So our continued proof, we know that cosine of theta is 9 over 41 from the previous slide, from the work that we have already done. So I also know that cosecant is 1 over sine theta. I need to find cosecant and I need to find sine here. Cosecant is the reciprocal identity of sine. Now, I've got sine and I need to I've got sine and I need cosecant and sine, but I don't need cosine, but it's something that came from my previous work. So if I have sine and I also have cosine, that's a big hint to use a Pythagorean identity. So observe that sine theta can be found by using the Pythagorean identity. Sine squared theta equals 1 minus cosine squared theta. That's the Pythagorean identity that I'm discussing here. So I'm going to find sine in the same way. I'm going to plug in and substitute my value of cosine that I know that was from our previous work. I'm going to say sine squared theta equals 1 minus 9 over 41 quantity squared. That's just by straight substitution. Then I'm going to perform a little bit of algebra magic here. We're going to square 9. We're going to square 41. I get sine squared theta equals 1 minus 81 over 1,681 just by squaring that quantity. Now I'm so dang close to finding out sine. I want to combine 1 minus 81 over 1681, and doing so with a common denominator, I get sine squared theta equals 1600 over 1681. And then I get to take the square root of both sides. I'm so close. So the square root of sine squared theta gives us sine. The square root of 1600 over 1681 is 1600 over 1681. And this further simplifies to sine theta is negative 40 over 41. Again, notice that we're in quadrant 4, so all students take calculus. Only cosine is positive there, cosine and secant. So I don't have cosine or secant right now, I have sine, so sine's going to be a negative ratio. Lastly, if I have sine, I know that sine and cosecant are reciprocals. That was that little piece of information that I set up here that kind of seemed insignificant at first. So if I know sine of theta is negative 40 over 41, cosecant of theta is going to be the reciprocal, or 41 over 40, since they are reciprocal functions. So I have my last 2 functions in all of the trig things that I was looking to find. Woohoo! We did it! That's the crowd going wild, in case you guys weren't sure. But yeah, so I know that went kind of fast, but I hope that me taking the time out to type all of this stuff out and also all of the reasoning on the right-hand side is helpful. I'm kind of still toying around with if I should make the videos of me like handwriting them out or doing the slides like this. It is a lot to type out, especially because I'm used to using Google Slides and I was having some issues with typing in my LaTeX code for this. For whatever reason, it wasn't rendering and it was really annoying. So I had to go to PowerPoint. And PowerPoint, I'm just not as well versed in. But I hope you guys are liking how I'm demonstrating these. And since we only had 2 examples today, y'all got time to practice. So this is homework 3. It's not due until Sunday, as is all of our assignments. So I gave you guys all 5 problems of writing in functions in terms of one another, since those really aren't too bad. And honestly, the more practice that we get, the better. And then I gave you guys 4 problems of quadrant analysis, just like that last one, where you are going to need to find all of the 5 other trig functions given one specific one. Yeah, so that's all we have today, cool cats and kittens, and I will see you Wednesday. Wednesday is when I'll see you. Remember, I host office hours on Fridays in case you guys have any questions, comments, concerns. And I'll probably put a survey up for you guys soon, just to see which method you prefer. Alrighty, talk to you later. Catch you on the flippity flop. Bye.